I will present you how to do a semantic search engine with LangChain. But first, let's dive into the subject by talking about semantic search in general. So semantic search can be opposed to a keyboard-based search, which is what we call lexical search, or we can qualify it as the traditional search. Keyword-based search means looking for the exact match of words in a document. For instance, it's like doing a CTRL F on your computer to find the word you are looking for in the professor's slides, for instance. So if I am looking for the word LLM in a document and I do a keyboard-based search, the results will only contain the exact word LLM, and the slides mentioning large language models in full letters won't be mentioned in the results. That's where semantic search is different because the goal is to search based on meanings and not just on the word. A semantic search engine will convert my query into a mathematical vectors to capture its meaning and then search for passages in the document that talk about my query in general. So now let's see how it works and how LangChain can help us creating a semantic search engine. And the entire process of semantic search can be divided in 5 steps. First, loading the document and returning documents objects, then splitting the documents, then doing the embedding, and then storing them in vector stores, and then returning the answer thanks to retrievers. But we will dive, we will try to understand the concepts together step by step. So the first step is about document and document loaders. So document loaders are designed to load data from various sources such as PDFs, but also web pages, Google Drive, social media platforms such as Twitter, Reddit, WhatsApp, and also other messaging services. And these document loaders will return a document object. For instance, for PDFs, they will return one document object per page of the PDF. So it's really useful when we are looking for a simple representation of the text from a PDF. But we have to be careful because for the PDFs, it will not parse the text which is coming from images, because sometimes in PDF you can have images in which some things are written, but the document loader won't be able to read from these parts. So the PDF must also not be a scanned article. It must really be only text on the page. So for each document object, each page of the PDF, we can then easily access the content of the page and the metadata of the page. So the file name, the page number inside the document, inside the original document. So a document object is described by 3 attributes. Page content, so it's the string with all the text of the page. The metadata, so it's a dictionary containing information about the source, the name of the original document, and there is also sometimes an ID attribute, which is a string to identify this specific document. Then we need to retrieve some information coming from the page. It's our goal. So to allow question answering purpose, because our goal here is to be able to retrieve document object pages that answer a certain query. But we can see sometimes these pages are too long and we only want to have the relevant portion of text that answer our query. We don't want to have all the text. So document splitting is really a crucial part of the work. And for that, we will use text splitters. And this technology splits the text in smaller chunks based on characters, for example. So splitting documents allows to deal with model limitations because many models have sometimes a maximum input size. We can't give them a large text. So splitting allows to process documents that exceed these limits. And it also allows for more memory efficiency, and it also allows a better parallelization of tasks. So many approaches are possible for text splitting. It can be length-based. It means that we can choose the size of the text chunks we are going to have. For instance, we can make the chunk the size of 500 characters or 1000 characters. And we also can make the chunks overlap, like an overlap of 200 character or 100 character, for instance. So we ensure that we don't cut a sentence from the rest of the relevant paragraph. So all the chunks are like superposed, like they overlap between each other. So, and we can also choose to split the documents following some separators, such as new lines, for instance. So yes, the split can be made based on the text structure because some splitters can keep a paragraph intact. When it splits the text, it can see the paragraph and split at the exact end of the paragraph. And it can also split following the structure of sentence, like regarding the dots at the end of the sentence. For some documents, the split can also be made based on the document structure, as some documents have a special structure, such as JSON files or Markdown documents. So the text splitter will split based on the special characteristics of those documents. And sometimes it can also be semantic meaning based, and this is the only method that considers the actual content of the text by analyzing the text semantic. But in our example that I will present you later, we will use a length-based split. And so now the idea is to associate numeric vectors to the various partition of the text we have, to the various chunk of text. And so we are going to use an embedding provider, and many of them are supported by LangChain. And these models are specifically designed to convert text into numeric vectors. So embeddings make semantic search possible because both the query, the question will ask our model, and the document object can be compared in a vector space. And it also allows us to find a relevant result by the meaning and not just by the words. So all these steps that we've done for now means that now our text is divided in small parts, in small chunks, and we want each of them to be represented as a vector thanks to the embedding, which means that text with a similar meaning will be geometrically close in the vector space. Then our semantic engine is working, and when we will do a query, we can see it on the graph, on the image on the slides. When we embed our query, we will use a similarity matrix to compare this query vector to all of the text vector we know, and we will compare them thanks to similarity matrix, as I said. And two vectors that will be close from each other will be related. And some similarity matrix we can use are cosine similarity, or sometimes, so cosine similarity is the one that OpenAI uses in their embeddings, but also it can be the Euclidean distance between the two vectors to show that they are quite close and they share the same meaning sometimes. So now we'll have, once we have our embeddings, we just embedded our text chunks into vectors. We need a place to store them and to search through them efficiently when we will ask our search or our semantic search model. So the vector store is a special type of database which is designed to handle vectors instead of plain text, for instance. So we will store our vectors locally sometimes, or we can also host them if we want through a provider. And we have to instantiate it at the beginning and index all the documents after, all the vectors. And we'll then be able to query it. That's our goal. And then when we will ask the question, the vector will compare the query, the vector of our query, and the result will be the relevant documents, so the most similar document chunks, the ones that are semantically closest to our first query. And now we can talk also about retrievers, because once our documents are stored in the vector database, we may want to have a simple way to get the documents back, and that's why we can use retrievers, because a retriever is a method that accepts a query and returns a list of the most relevant document objects. And this list also returns the two attributes of the document object, the content of the page and also metadata, like I spoke about it before, the metadata associated with the document object, like the file name, the source, for instance. And there are many different types of retrievers, but a vector store can act as a retriever, for instance. So now that I presented to you all the different steps of semantic search, of a semantic search engine, I will show to you what we can do thanks to LangChain. So I'm just gonna say, I forgot to show one of the pages, sorry. So we will do a semantic search over a PDF file, and the document we want to analyze today is a 2023 business report from Nike, but it's like it's 107 pages long document, so we don't really want to read everything in this document. So that's why we will ask our semantic search engine to find information for us. So that's the document. Like we really don't want to read everything, and that's why LangChain will help us. I think you still can see my screen, so yeah. So our goal is to first load the documents using PyPDF. So here is so I had to first upload some packages for the script to work. So first I am giving the model the URL, and then I can load it thanks to PyPDF. So each page of the document will then become a document object, as I said before, and we can then print the number of document objects, which is equal to the number of the pages in the PDF, so 107 here. Then we will split no, sorry, I skipped one part. We are I chose to show the beginning of the first page, the first page content here. You can see, United States, Nike. And then I also show here the metadata of the first document, of the first page. And we can say the creator, the creation date of the document, the author, and other things. So it's all the metadata. And then we can split the document using a text splitter. And so here I put chunk size, so it's a size, the number of character in each chunk, so it's 1000, and 2,200 character of overlap. And then we can see the number of chunks after splitting, so like 516. And here is an example of the first chunk, the content of it, and the metadata of the first chunk. We can also show it here. So then we will create the embeddings. It means, like I said before, that we translate each chunk into numeric vectors, so they don't mean anything to us if we try reading those vectors. Like it's like this. So the first document, it's vector 1, is becoming this type of thing. So it's a vector, so it don't mean anything to us, but for the model, in fact, it really means something. And in the tutorial, the first tutorial I saw, they did it with OpenAI embeddings model, but to use it, you have to have an OpenAI API key, which I don't have. So I found an alternative. I chose to play with Hugging Face embeddings. It's another embedding model, and it also works very fine. And so we translated all the chunks in vectors, thanks to this. So here we also can see that the vectors are 384 in length, so that's quite huge, but it depends on the embedding model. Sometimes the vector can be much longer or maybe a little bit shorter. And then we have to instantiate our vector stores to store all our vectors. And then we will be able to query it after. So that's what we've done here. And then we can start to use our semantic search engine. And for instance, we can ask our engine, how many distribution centers does Nike have in the US? That's a quite complicated question, and we don't want to read all the 107 pages of the document to know it. And let's ask our model. So LangChain will convert our query in an embedding in a vector, and we will use methods such as similarity search, for instance, that will give to the model the query string, and we will get back the relevant chunks whose embeddings are close to the embedding of our query. And we chose to print the first one here. So this is an embedding that answers our question. And we can see that the store are here. Brand inline store 74, Converse store 82. So we can see the total of distribution center that Nike have, 369. So we have our answer. And then we can also ask, so this was a synchronous query, but we can also do asynchronous queries. And we asked when was Nike incorporated, and we have our answer here. Nike was incorporated in 1967. So, and then we can also ask for the scores of similarity between our query and the answer that the model gives us. So we can see that here the score is 0.39, which is quite close to 0, but we have indeed our answer. What was Nike's revenue in 2023? And revenues were $51.2 billion. So we have our answer in this chunk too. And then we will yes, we can also do an embedded query here. How were Nike's margin impacted in 2023? And here we also have our answer. And so this answer in this part that I showed you, the example I just showed you, we don't use retrievers, but retrievers, oh, sorry. And retrievers made it more easily to make pipelines after. So here is also two examples of queries using retrievers. And the function batch here allows us to ask multiple queries in the same process. And so that's it. So we can see that our semantic search engine is working. We have our answers. We ask a question about Nike's business in 2023, and the model answers us. So to just conclude a bit, so we just learned how semantic search works. We learned that after splitting our original document in smaller parts and representing its text as embeddings, we can store the embeddings in the vector store, and then retrievers can help us find the most relevant parts of the original text to answer our query. So now we know how LangChain can help us implement it easily. That's all for me, I think. Thank you. Yeah. So I let Ricardo or Beatrice
Thank
maybe
you, Adèle.
before. Thank you.